Okay, everyone, we're back. I think things are working a little better than they were working yesterday. Our online friends can hopefully hear me and see me, as well as the slide. So once again, if you want the slides, here they are. So normally this course is about 8 lectures over 2 weeks, but of course this is condensed, so we only do a few lectures, just over a few days here. But I put all of the slides that I have online, so if you want all of the slides, you can get them here, and feel free to download them and ask questions and other things like that. So we took a vote yesterday. A good portion of you voted. What should we talk about today? It seems like there was a lot of interest in this field of astrobiology, so I'll talk a little bit about that today. And if there's some time left, I'll talk a little bit about the equation of state, because people were asking about that as well. Both of them are very difficult topics. And I will be giving a talk tomorrow as well on astrobiology as well. And so this will be kind of an introduction. And so what you can do is listen today and then come to the talk tomorrow and think of really hard questions to ask tomorrow. And all of your professors will think, wow, these people are really, really smart when they're asking all these hard questions. So, of course, we already know that, right? But this will give you a warm up here, okay? So if you are interested, a colleague and I wrote a book on this topic a couple years ago. It's okay. It's not a great book. Don't buy it on Amazon. It's way too expensive. It's horribly overpriced. If you want a copy, just email me. I'll send you a free PDF. It's yeah, it's just not a good book at all. So, all right.
Reverse psychology.
Yeah, no. Yeah, don't buy on Amazon. Way too expensive. Okay. What's that?
IOP. We complain with that.
Yeah. It's just way too expensive. It's yeah, IOP is a good publisher, but just extremely expensive. And so I always, whenever I write anything, I just give it away. And so, okay, so this topic is actually extremely difficult, and I can tell you, I got interested in this topic over 20 years ago when I was in graduate school. So I've been working on this for close to 23 years now, and have made very little progress over the years, just because it involves a lot of chemistry and a lot of biology and astrophysics. And I'm not a chemist. I'm not a biologist. I'm barely a physicist. And so it involves all those things together, and how physics and biology and chemistry relate to each other. And we would make some progress and then go for a few years without progress. Then we make some progress and then go for a few years. The last couple of years, we've been much more active, and we even got a grant for it. So now we have to do it. Now we don't have a choice. We've got to do it. So I'm going to talk about some basic definitions, and then talk a little bit about how nuclear physics might come into play here, and especially how astrophysics comes into play. And feel free to interrupt at any time. This is going to be more like a talk than a class, but of course you are very welcome to discuss anything you'd like here. So this is where I started many years ago, when I was yeah. So what you're looking at here is just a picture of an amino acid. Okay. An amino acid is just a carbon atom, and it has this object here, which is called a nitrile, or maybe an amine group. This is a carboxyl group. And then there's just some arbitrary chain on the side. And so is this familiar? We've seen these? Okay, so we know these. But because they're asymmetric molecules, they have mirror images. So I could take one amino acid and look at it in a mirror. In math, we call that a parity transformation. We reverse the coordinates, and they are just like your hands. Your hands are mirror images of each other, and I can't take my left hand and move it onto my right hand so that it looks like it's exactly like my right hand. Okay, and the Greek word for that is chirality, which means hand, because it means hands. And there's this amino acid down here. This is one of the simplest alpha amino acids. That's called valine, and that's in its two chiral forms here. So you can see that one is the mirror image of the other. Okay, and this has been known for a long time. These amino acids are optically active, which means that they behave differently with polarized light. And this was discovered by Louis Pasteur about 200 years ago. Being a true Frenchman, he extracted tartaric acid from wine and discovered that it was chiral. It had two-handed states. And he looked at some of the optical properties of these amino acids. This is Louis Pasteur down here in his two chiral states. Right. So that's interesting. I mean, that's okay. So chemistry. I never liked chemistry. It just doesn't interest me to see these sticks in these balls. But what did interest me is amino acids and other organic molecules have been found in space. Radio astronomy is really good at finding organic molecules, and the reason is because they vibrate at radio frequencies. They change their shape at radio frequencies. So nuclei work at gamma ray energies. We think of when nuclei get excited, they emit gamma rays. When molecules get excited, they'll emit radio waves and things. And so radio astronomy is really good at finding these things. And so here's a picture of the NAO, National Astronomical Observatory, 12-meter telescope. And they found organic molecules in Sagittarius 2b, which is that way. It's towards the center of our galaxy. And so they were just looking at dust clouds and things. And this was really interesting. So you could see vibrational signatures. And it's arguable whether they've seen amino acids or not, whether they've seen glycine, which is one of the simplest amino acids, or not. But they think there have been signatures of that. But we've also looked at meteorites and asteroids. And this has been a very, very important field these days. Glycine was discovered in comet tails. You probably remember this mission where an object landed on a comet, which I just was amazed by that. And then this recent mission here, this is the Rosetta mission. Excuse me, the Hayabusa 2 mission. They not only landed on a comet, an asteroid, but they brought back dirt from this asteroid. They brought back 10 milligrams of dirt. So $1 million, right? If you have a lawn, you might pay $10,000 for the lawn. They paid $1 million for 10 milligrams of dirt or so. And they are almost done analyzing it. There are some preliminary results coming out of it, and no papers have been published yet. But I can tell you now, some of my colleagues are working on that, and they found amino acids in the asteroid dirt, which is unbelievable. It's amazing. So we know amino acids can be made in space. These organic molecules. We're pretty sure methane. We weren't really surprised that methane could be made in space because methane is a very simple molecule.
Methane.
Yeah, methane. NH. Yeah. And okay. CH4. Yep. So we're not surprised at it's a very simple molecule. It's symmetric. Pretty easy. We're not too surprised that water, which is not organic because it doesn't have carbon in it, is made in space. But now we can assemble some more complex molecules, and there's been things like alcohols and other things made in space, which is particularly interesting. So that's what I would say is interesting fact number one. Okay. Interesting fact number two is this this dumb rock. It's just a stupid looking rock. Okay? If I saw this rock on the street, I would kick it out of the way. All right. I think the rocks on Via Etna are much more interesting. So, but this rock fell onto Australia in 1969. This was a piece of a famous meteorite called the Murchison meteorite. They found amino acids on this rock. They found amino acids in this rock. Probably one of the most extensive studies of amino acids in meteorites ever. There have been other studies that follow, but this one, people have been studying this over and over and over again, and they perfected their work. This was really one of the ones that opened up the field. You need to have a couple definitions. We define this. So amino acids are chiral. So they have a left-handed kind and a right-handed kind. And it's a convention, which one we call left, which one we call right. In fact, if you go to the NASA webpage, the United States NASA webpage, they have a similar picture of the hands with the amino acid, but it's very confusing because the hands are backwards and the amino acids are not. And so I had to look at this for 2 weeks and was very confused. And is it somebody giving me the amino acids, or is it somebody standing like this? Why would you do this? It's a convention. Right? But we define this. This is called enantiomeric excess. One hand of an amino acid is called an enantiomer. Just vocabulary. But we define this, the amount of left-handed minus the amount of right-handed over all of the amino acids. It's an asymmetry term. We see this a lot in physics. We use this term a lot. So if I had an equal mix, right? If I make amino acids in the laboratory, and of course we can do this. When you buy energy drinks and things to help with weightlifting, you buy these big buckets of powder with amino acids in them. If I were to make it in a laboratory, the easiest thing would just be to make equal amounts of left and right-handed amino acids, because if I just mix it up, that's what would come out. Okay. What would the enantiomeric excess be of equal left and right? 0. Yep, 0. And if it were all left-handed? 1. And if it were all right-handed? -1. Yep. All right. So it's a scalable number. Okay. So here's the interesting thing. Here's interesting fact number 2. Interesting fact number 1 was that amino acids have been found on meteorites and in comets and in space. Interesting fact number 2 is this. All right. All life on Earth only uses left-handed amino acids, okay? With a few notable exceptions, which I'll mention later on. But the grass, you, me, the trees, animals that we eat, vegetables that we eat, mozzarella, all has left-handed amino acids, okay? In fact, if I were to eat a right-handed amino acid, at best, it would be completely useless. At worst, it would kill me, okay? I'm sorry? Oh, I thought I heard a question here. By the way, companies that make these energy drinks, like Red Bull and Monster, it says it has the amino acids in it. I don't think they know this, okay? Because why would they know that? So I'm terrified to drink these energy drinks because they could be right-handed, right? Now, here's interesting. That, by the way, that term is called biomolecular homochirality. This is one of the biggest questions in biology today. How did that get to be that way? If you look at the National Academies of Sciences, they listed some of their top questions in science. This is one of the biggest ones. Okay. Now, interesting fact number 3 is why I really got interested in this, and that's the following. Meteorites have been found to have predominantly, not 100%, but predominantly left-handed amino acids, which is really interesting because if I were just to make an amino acid, it could be left or right with equal probability. But we found that meteorites, at least this meteorite, has mostly left-handed amino acids on it. And it has some complicated ones on there as well. Now, there are some meteorites out there that don't have all left-handed, that have an EE of 0, it's equal left and right. But for the most part, the meteorites we've looked at are predominantly left-handed. We expect them to be equal amounts, but they're not. So this tells me that there is a process that exists in space that can select left-handed amino acids. And could that process somehow be related to the amino acids on Earth? Okay, so there's some theories out there, and I'll talk a little bit about that. So here's an example of amino acids in meteorites. Take a look. Valine here. Valine does have a few more right-handed amino acids on that meteorite, the Murray meteorite, but the rest of them are purely left-handed. This one also is interesting because the error bars on it are quite big. Okay, so that one may just be 0. But isovaline is particularly interesting because it's not made on Earth. Okay, so when we see isovaline in meteorites, isovaline is not made naturally on Earth. I can easily make it in the laboratory, right? But it's not made naturally on Earth, so there must be something in space that can make it. It was carried to Earth on meteorites, so there must be something there that was able to create it. And the reason that's important is because if a meteorite lands in the middle of a field and a bunch of, let's say a bunch of little kids run out and they grab it and they toss it back and forth and they play it and they lick it and things, it's probably going to get amino acids on it just from contamination. So it's kind of important that we found isovaline. And this percent, so sometimes we say percent for enantiomeric excess, plus 100%, minus 100%, 0%. This percent is predominantly left-handed. Not all the way, but predominantly. Okay? So that's interesting. That's interesting. Fact number 3, and this is how I got interested in this topic. Do note that these amino acids on meteorites are not homochiral. It's not 100%, but it's not 0% either, which is really an interesting topic. Okay? So why is this interesting in the field of astrobiology? And by the way, when we talk about astrobiology, it's a very, very, very big field. It includes exoplanet searches. So right now we are discovering on average 1 exoplanet every day. It includes habitability searches. So we try to find planets where humans can live, which I think is kind of scary because if humans go, we might ruin that neighborhood too. So, but that's just me. It means we look for life in other planets. It means we look at biochemistry in space. Part of astrobiology is also the search for extraterrestrial intelligence. So it's a very large field. This is just a very, very, very tiny part of the whole field. Okay? Let me show you something that's quite compelling in terms of the history of the Earth. All right. Do you know what this is?
It's the tree of all living species.
Yep.
From Archaea to the mankind.
Yep, that's exactly what it is. Yep, very good. Yeah. And by the way, this website here is really neat. Down here, this website is a similar one, but you can zoom in and out and you can click on things. Yeah. So this is the the tree of life, sometimes called the phylogenetic tree. Think of it as a circle. The radius of the circle is time. So as you go from the center here, you're going forwards in time. So this is about 3.5 billion years ago when the first bacteria came on Earth. And this is the present here. And then you can see some gaps where there were major extinctions and things like that. You can also see what were called explosions, where we got many, many more species. So you had a Precambrian explosion and things like that. So why am I showing you this? Because about 3.5 billion years ago, during that shaded area there was a major meteoric bombardment of the Earth. The Earth was constantly battered by meteorites. Okay, it's seems reasonable that life couldn't form at that point because the Earth was just a terrible place to live. But life formed shortly at the tail of that bombardment. This is when the first bacteria and things started coming out. So there have been theories, and I'm not sure if I believe this or not, but there are theories that this idea of biomolecular homochirality was triggered by meteorites. Okay, meteorites had some left-handed amino acids on them. They brought them to Earth, and then life had an imbalance. And one thing about life is, and biochemistry, is it can take little imbalances and drive it all the way to 100%. That's sort of why you and I exist today. And so there's this theory that maybe modern homochirality, modern molecular chirality was triggered by the last meteorites to hit the Earth as life was just getting to be formed. Well, that would be like panspermia, which is another theory, but somehow maybe that chirality was triggered somehow. Yep. So it's an interesting theory. I'm not sure if I subscribe to it or not, but we can at least say that there is a process that can make left-handed amino acids, and that same process can work in space. Or there may be multiple processes. But regardless, there is a physical process by which left-handed amino acids can be made. Okay? So here's a cartoon. This is a cartoon of just kind of what's going on, sort of a cartoon of this is how a physicist looks at the history of life on Earth. You have this what we call this prebiotic soup. That's a evolutionary biology term. Just all these organic molecules and lipids and proteins ready to make life. Okay, and it was influenced by many things. It could have been influenced by meteorites. It could have been influenced by chemical reactions. Was influenced by biological reactions. There's some sort of interaction here. And from these biological and chemical interactions, we formed the very first bacteria, the very first single-celled organisms, and then from there, life took off. Okay, so real simple view there, but do note that there is a possibility that somehow the meteoric bombardment maybe didn't form life on Earth, maybe didn't bring amino acids to Earth, but might have tipped the balance a little bit in one direction or the other. Okay, I am certainly not the only person to study this. Here's a chart of the different models that people have for how amino acids got to be left or right-handed. And these models vary from just random stochastic processes, and those could be things like formation of crystals, crystallization of amino acids onto a surface, could just be some random process or something like that. And then there's what's called these deterministic processes, and these are processes that drive it in one particular direction. Okay. These involve things like chiral fields, which would be something like circular polarized light, or some parity violating mechanism. And this is where the physicists do really well at. Anytime we see something in science that is imbalanced, or anytime we see an imbalance in science, the physicists always want to go towards the most fundamental imbalances we can think of. And of course, the parity violating weak force is one of the most fundamental ones in the universe. It was formed during the first fraction of a second. The other fundamental imbalance in the universe is that we are all made of matter. Okay, there might be another universe out there that thinks we're all made of antimatter. They're just weird. Okay, so yes, question.
Does the particle handiness, like the left-handed neutrinos or something like that, influence the chirality of the molecules?
I don't know. but I'm going to talk about that.
Okay.
That's what I'm probably going to spend most of my time on. In fact, that's the project that I've been working on right now is there a relationship between the fundamental nuclear physics and the chirality of molecules? Because whatever happens to make left-handed molecules must work in an environment where the biochemistry, well, first of all, there's no life, and biochemistry is at a bare minimum. Okay, so I'll talk a little bit about that. I'll talk about some physical mechanisms. I'll give you, go through some of these mechanisms here. The one where I'm going to spend most of my time is this one here. The parity violating weak force. Does that have an effect? Okay. I'm not sure. The more I work on it, the less I believe it. But that's good science anyways. Good science is always throwing out your pet theories, right? So, by the way, here's another very good book. Very, very good book. In fact, this book is better than mine and less expensive as well. So if you're interested in some good reading, that's a good book right there. Okay. He goes through several mechanisms. He's a world expert on the topic. He spends most of his time looking at the chemistry. I spend most of my time looking at the physical results. Okay. So I'll go through a couple different possible effects really fast, just to give you a flavor for some of the things people have looked at. Okay. One possibility is optical dichroism. Polar molecules, chiral molecules have dichroism. Okay. What that means is light with different polarizations will pass through the molecule differently. It will be diffracted differently. It will be absorbed differently. So if I have a polar molecule here, this looks like norvaline here, an amino acid. And I send left-handed circularly polarized light through it, it will be absorbed differently than right-handed circularly polarized light. Okay. By the way, do we know what polarized light is?
It's light that is being cut into just a direction of propagation.
The electric field
The electric
vectors only oscillate in one direction in polarized light. Yep. So for linearly polarized light, the electric field can oscillate like this or like this. Okay. For circularly polarized light, what happens is the electric field and the magnetic field are out of phase a little bit.
Like in the like sine and cosine, for example.
Yeah, exactly. Yeah, which way is it oscillating? So in circularly polarized light, the electric field does this as it propagates. That's for left-handed, for right-handed circularly polarized light, it does this. It oscillates the other way. Okay, so the electric field, like a helix, yeah. And I'll show you a better picture in a second. So there's that possibility, and it's actually a pretty good possibility. And in fact, we're pretty sure that is one possible mechanism. Okay. Another possible mechanism is what's called magnetochiral dichroism. So dichroism just means light is absorbed differently if it goes in one direction or if it's polarized in one direction. This was studied by a physical chemist in England called Lawrence Barron. He's also a really neat physicist and great mathematician, where if you apply a magnetic field to something, then light moving in one direction will be absorbed differently than light moving in another direction. Now, it's a little tricky how that applies to organic molecules, but because organic molecules are optically active, that means they absorb light that travels differently depending on the molecule. This could be a possible mechanism as well. Okay. Now, getting back to the circularly polarized light, here's a picture of it, the upper left corner here. There have been studies on the effect of circularly polarized light on amino acids. So there is that possibility. Okay, and they do experiments that look like this. Okay, they just take an amino acid, they take circularly polarized light, and they shine it on the amino acid, and they see how much is left when they're done. This is what's called a selective destruction mechanism. It destroys one amino acid more than it destroys the other amino acid. Okay. And this was a really good work. They did some great work on this. They found, yes, indeed, circularly polarized light can produce an imbalance in the number of left and right-handed ones. There's a couple questions about this experiment. One is it produces a very small imbalance, even for a very intense polarized light. Okay. The other thing is you have to tune the light frequency really tightly. Okay, so take a look at these figures on the right-hand side. Think of this x-axis as the imbalance. Okay, how much left or right-handed amino acids we have. Okay, and this is a very small number. These are something like 10 to the minus 4 or something like that. And this is how much of an imbalance you have as a function of the light wavelength. Okay, so take a look. This is ultraviolet light. These are very narrow bands. So if the light wavelength is about 180 nanometers, you get a positive EE. If the light wavelength is about 205, you get a negative EE. So very narrow bands. Okay, it would have to be monoenergetic light. It would have to be light all of one color. Okay, but it does work. It does work. And so there's some theories that maybe in space, if you have regions of polarized light, you can get this. Of course, the difficulty is that the polarized light spectrum isn't necessarily very narrow bands. The polarized light spectrum covers this entire region and more. And so you might get some things washed out, more or less. But it is possible. It is possible. Circularly polarized light can be produced by what's called Mie scattering in dust. That's just light that scatters off of dust particles, becomes polarized. Okay, generally I think spherical dust. Mie scattering is scattering of light off of spheres. And by the way, you see polarized light all the time. Okay? The glare on this table is polarized. So if you have polarized sunglasses, you can take them and look at the glare on the table and rotate the sunglasses, and you'll see the light get darker and lighter. Okay. Another difficulty.
You can do this with the seawater.
Yeah, but the seawater is a great example because there's a lot of it out there. Where I come from, we see polarized light when it comes off the ice on the roads, just before we crash. One major difficulty with this idea is that polarized light, of course, doesn't penetrate surfaces. And we found amino acids deep inside meteorites, right? Which means they would probably have to be processed either before the meteorite comes together, or there would have to be some other process that does this, okay? And this, by the way, is this is just a map of space. This is how we detect polarized light in space. This is, I believe this is in the Orion Nebula, regions of polarized light. So certainly polarized light exists in space. Certainly we can see it, okay? So certainly not impossible. And as we just said, polarized light exists on the Earth. Light that's scattered from the sun is generally polarized, okay? So that's a possibility. There's another chiral molecule, and this is where I'm going to spend most of my time talking because this is where physicists can really do some studying, and that's weak interactions, right? So weak interactions involve electrons, muons, taus, and neutrinos. Okay? Somebody already asked, could left-handed neutrinos have something to do with it? And that's what I'll spend a little bit of time discussing. Okay? This is not a new model at all. This was proposed many years ago. This is called Vester-Albright hypothesis. This was proposed in 1953. Maybe polarized electrons from beta decay can induce a selection of one amino acid over the other. Right. Before we get into that, I'm going to get into some basic nuclear physics. Okay. So pretty simple. You've probably heard this before, but it's worth repeating. Particles have spin. Okay. Now, when we think of spin, sometimes you think of a top that's spinning on a table. We think of quantum mechanical spin, which sometimes behaves like angular momentum, but sometimes it behaves a little differently. Okay. Quantum mechanics, you almost have to unlearn everything you've learned before. But when we think of spin, it still has units of angular momentum. Okay. We can think of a particle as having spin up or spin down. Sometimes we say spin +1, spin -1. Here's some chiral cats. Okay. All right. A couple other definitions. Leptons. We've used the word leptons before, but let's remind ourselves. Leptons are like electrons and neutrinos, muons. There are a lot of leptons in cosmic rays. They have spin 1/2, so they can be what we call spin up or spin down. Okay. Nucleons. Nucleons like protons and neutrons. This is wrong. This is wrong. How did this end up here? Forget this statement. This is completely wrong. Okay. It should have said nitrogen, but I probably missed a line here. Nitrogen has a spin of 1. Okay. What that means, it can have 3 spin states. It can have up, down, or 0. Okay. Not nucleons. Nucleons have spin 1/2. Okay. This probably should have said nitrogen. Okay. Units of spin is in units of Planck's constant over 2 pi. Okay. All right. So that's angular momentum in particles. They carry angular momentum. When they interact with each other, they can trade angular momentum back and forth. How they interact depends on their angular momentum. Okay. Let me give you another definition here. This idea of helicity, someone already mentioned it. So helicity, we define as helicity. It's the dot product of a particle's spin and its momentum vector. Sometimes we use sigma. Sometimes we use a little s for the particle spin. Okay. So what it means is if a particle is moving in one direction, we use the right-hand rule. Are we familiar with that? Okay. We can use the right-hand rule to determine which way its spin is, up or down. If its spin is in the same direction that it's moving, then it has a helicity of 1. If its spin is opposite the direction that it's moving, it has a helicity of -1. Okay. Now, this is a little confusing sometimes because helicity and chirality are not necessarily the same things. Okay. Can you think of a case where helicity can change?
The particle changes its momentum.
Possibly change in momentum. Sure. Even simpler, if I'm an electron, and let's say I'm not relativistic, but I'm spinning, I have helicity, okay, and I'm moving in this direction, and let's say I have spin in that direction. What if another electron comes moving by it at a faster speed, right?
It collides with it.
Let's say we don't even collide, we just move by it.
Oh.
According to this electron is now moving that way, but its spin is still that way, okay? So helicity is not the same as chirality. For neutrinos, it's a little easier because as far as we know, at least for the purpose of this, how fast do neutrinos move?
Almost in the field of light.
Yeah.
Almost.
Yep. And for all intents and purposes, we can just say the speed of light. All right. And that works for what we're doing here. Okay. So relativistic leptons, neutrinos, for example, have a definite helicity, right? What's the helicity? Yes, question.
Does the spin, does the spin need to have the same axis as the momentum? Because if so, the helicity has to be 1 or -1. Can it be something in between?
Can it be something in between? Yeah, that's a really good question. It depends. For something that moves the speed of light, the helicity has to be, if it has a spin 1/2, spin 1 or -1. Okay. For non-relativistic particles, so let's say I just have a nitrogen nucleus and it's thermal, it's moving. It doesn't have to be. It doesn't have to have a definite helicity. Okay. That's the magic of quantum mechanics. By the way, this idea of what we call definite helicity would be, you probably take that in you might take it in grad school or as a senior grad student. Those are called Dirac particles. Okay, but particles where we not only determine their momentum, but their spin states as well. Okay. Okay, take a look here. Take a look at this top particle here. Its spin is pointing opposite the direction of its motion. So that spin vector, that's S right there. Okay. Its velocity is this way. This is a left-handed particle and -1 helicity. Again, a convention. This down here, the spin is in the same direction. That's a right-handed particle. A lot of times in physics, we use L and R. Chemists really confuse me. Chemists are like astronomers. They confuse me. I try to use L and R for left and right. The chemists will always use, I believe they always use L for left-handed, but for right-handed, they'll use D. And I believe they'll use S, if I'm correct. Okay. I know they use D. This is from the Latin word for. Okay. I figured you guys would know some Latin, right? Yeah, yeah. Okay, so one other thing we want to talk about here is magnetic moments. Okay? Like a magnet, like a compass needle. Okay? Particles that have a spin can have a magnetic moment. Okay? I say up here, particles with charge and spin have magnetic moment. That's not entirely true. You can have 0 charge, but still have a magnetic moment. How can that be? Yep, you can have 0 charge, but have a non-zero magnetic moment.
Because you have to,
Neutrinos have 0 charge. Neutron has 0 charge. What makes a magnet? Dipoles, yeah. You can make a magnet by wrapping a wire around a nail, right? And putting a current through it. Moving charge, right? Moving charge. What's the net charge in that wire though? 0, right? Yeah, the wire has 0 charge, right? So magnetic moments are really determined by the charge distribution, how the charge is arranged within a particle. Okay? So generally, we think of particles with charge having magnetic moment. You can also have 0 charge as well.
Does it have something to do with the quarks?
At that level, it could, although I don't know how. I'm sure it does. I just don't know the math for that. So, yeah. Okay, they behave like compass needles, and then you can see that, of course, particles with magnetic moments can orient themselves in magnetic fields. Okay, there's a lot of other things going on, but generally that can happen. Okay, in fact, you've seen it all the time when you use a compass. Okay, and it's related to the spin through what we call the gyromagnetic ratio. That's just a term, that's vocabulary. Okay, the ratio of the spin and the magnetic moment. Okay, and we use this principle all the time in NMR, nuclear magnetic resonance. Hospitals use this every day when they do MRIs.
It's interesting. In Italy, we draw N. It's we call it risonanza magnetica, but we omit nucleare because this is a bad sounding word.
Yeah.
Chernobyl, at least.
Yeah. This is why I'm sure this is why hospitals use MRI, the magnetic resonance imaging. In the U.S., we call it MRI, magnetic resonance imaging. This, by the way, if you go into nuclear physics, I'll just give you a hint. If you're going through security at an airport and they ask you what you do, just say you're a scientist. Don't say nuclear; they get touchy. So. Right. And if they say what kind of scientist, say you're an astrophysicist. Then they leave you alone. Okay. All right. Here's a couple definitions. So amino acids have oxygen, carbon, nitrogen. One amino acid has sulfur in it. Oxygen and carbon, at least in their ground states, have zero spin. Okay. So as far as we know, they don't have any preferred spin alignment. Okay. Hydrogen has a spin 1/2. So it's also got a non-zero magnetic moment. Hydrogen its spin can align in a magnetic field. Okay. Nitrogen as well has a spin 1. Its spin can also align in a magnetic field. In a very strong magnetic field, you can think of those as having a non-zero magnetic moment. Okay.
Because they are charged.
Because they have a charge and a spin. Yep. Okay. Neutrinos and antineutrinos are truly chiral. Okay. And I'm assuming that they have no mass. Of course, you know that they have a tiny amount of mass, but it's gonna be negligible in this case, right? So all antineutrinos are right-handed. All neutrinos are left-handed. Okay? They all spin the same way. This, by the way, was discovered a long time ago, and I should have shown you a picture here, but. One of the most interesting experiments in physics, it's called the famous Wu experiment. Just look that up. She did an experiment with beta decay where she looked at the electrons and she put a nucleus in a magnetic field, and she was able to look at the electrons coming out one way or the other. She aligned the spin of the nucleus. She remembered that angular momentum is conserved in nuclear reactions, and she was able to contribute to the knowledge. And this is why we say weak interactions are parity violating. They look different if you run them in a mirror. Okay. Okay, remember I told you, I guess it was last week, if you have a nuclear reaction, what's conserved? Well, mass has to be conserved, baryon number has to be conserved, energy, momentum, angular momentum has to be conserved. Okay, take a look at this really simple reaction here. And for now, let's assume that I'm just doing a reaction between nitrogen-14 and an antineutrino. It could be an electron. It could be a muon, it could be a cosmic ray muon, but for now, let's just assume a neutrino, because neutrinos are definite helicity. It kind of makes the reaction simpler, okay? Nitrogen has a spin of 1, and let's assume that we arbitrarily set our coordinate system so that the nitrogen is always spin up, and then we interact with a neutrino. depending on the direction that that neutrino is going towards the nitrogen, it can have forward spin or backward spin. Okay. Well, this is called inverse beta decay, by the way. I'm sorry, neutrino capture. It makes carbon-14, okay, plus an electron. Okay. Now, the spins all have to add up, right? Spin has to be conserved. Angular momentum has to be conserved. If I have a spin up and a spin down, spin up 1, spin down -0.5, then my total angular momentum is 0.5, right? Which means my electron has to come out spin up. Okay? They're just simple conservation.
And
Yep.
this anti-reaction is used to detect neutrinos.
I don't think we use nitrogen. I think we'll use things like chlorine and argon, and sometimes the neutrinos interact with iron in the rock and produce neutrons. But it is, I mean, it's a similar thing here. The neutrinos just interact with the tank of water or gas or something. It's a huge field of science, by the way. Yep. I'm picking on nitrogen because nitrogen is in amino acids. Take a look at this bottom reaction. So what's the total angular momentum on the left-hand side of that equation? 3/2, right? The electron has an angular momentum of 1/2, okay? Which means there has to be some angular momentum that comes from somewhere else. No, it's just the electron has to carry away its own angular momentum. All right. Do photons have angular momentum? Yep. Spin 1 on a photon. Yep. Could be. And but somehow we've got to figure out where that extra angular momentum comes from. As it turns out, because of the rules for this kind of reaction, this top reaction is much more prevalent than the bottom reaction. Okay, the bottom one is suppressed generally by about a factor of 1,000 or so. And you'll hear terms like forbidden transitions or something. They're not not forbidden like you can't do it. It just means they occur at a very, very, very lower rate. Okay. So if I were looking at these two reactions, this one would occur more often. Okay. Now, it doesn't have to be neutrinos. It could be spin polarized electrons, and spin polarized electrons have been studied before. It could be spin polarized muons. It could even be photons. A different set of rules, but you could do that as well. So it could even be an electromagnetic transition. So if we can think of a way to orient a nitrogen molecule, and we have a source of spin polarized particles, then we can select one reaction over another. Okay, and if we can somehow destroy that nitrogen molecule within an amino acid, we can destroy the whole amino acid, right? And that's possible because molecules are held together with energies of like single electron volts or a couple electron volts. The recoil, think about bouncing pool balls off the nitrogen molecule. The recoil of the nitrogen molecule would be something like thousands of electron volts. It would just fly out of the molecule. It would destroy the molecule. Yes.
You drew a carbon-14
Yep.
saying it has no angular momentum, but does do all carbon-14 zero angular momentum?
All carbon-14s in the ground state at 0 angular momentum. It's possible you could have an excited level of carbon-14, which you might excite a proton up to some orbit or something like that. Yep. All right. So this, in my mind, and scientists have been looking at this for a while, this is one way of coupling molecular chirality to the nuclear physics. There could be a nuclear process that somehow selects the chirality of the nitrogen-14 nucleus in an atom, or even the hydrogens, I guess. This one's got the biggest effect, however, to a source of spin polarized leptons and destroy the molecule by destroying the nitrogen. But of course, there's a big problem. There's a big problem. nuclear spin is not molecular chirality, right? You have this nucleus sitting in the center of a molecule, and it can more or less just orient itself any way it wants. Okay? So the question is there a way to couple the nuclear spin to the molecular chirality? And it turns out the answer is yes, and it turns out we've been doing this for 100 years. We talked about it a few minutes ago. Nuclear magnetic resonance, or magnetic resonance, if you will. So the reason nuclear magnetic resonance works and the reason why it's so popular in medicine and chemistry is because you are not just looking at the spin of a molecule in a magnetic field, you're looking at the effects of the molecule on the spin. So for example, if I put some arbitrary nucleus in a magnetic field, and let's assume there's no electrons, we say it's unshielded, it's going to have a magnetization, okay? If I put a whole bunch of them in a magnetic field, I can measure what I call the magnetization. Which way is the net magnetic moment of this nucleus? But we know that nuclei don't exist in vacuums. Nuclei in molecules are surrounded by electrons. So if I put a nucleus in a magnetic field and then I add all the molecule around it, those electrons have momentum. Those electrons are moving. Those electrons also feel the effect of the magnetic field. It's very much like, I'm not sure if you've studied it or not, but it's very much like Lenz's law. Okay? Are we familiar with that? You might have studied it. It's kind of like that. The electrons will be affected by the magnetic field and almost effectively set up their own counter field. So the magnetization of nuclei in a molecule is actually changed. It's actually less than if it were out in space. Now, this is actually pretty tricky because it's a three-dimensional molecule, right? Molecules have multiple dimensions, and if I have some magnetic field, all of those electrons are moving in strange orbitals. And now, when you start to do molecular chemistry, it's a lot harder than just looking at an atom. The electron momentum surfaces are really weird, and I have a magnetic field. Those electrons are going to change the magnetic field at the nucleus, but not necessarily in the direction of the magnetic field. There could be a change to the side, one way or the other. Okay? It could look something like, yeah, let me walk you through it. I already showed you this. I have a bare nucleus, no NMR. There's going to be more nuclei that are spin up than spin down, depending on the strength of the field. Okay? However, when I add the electrons from the molecule, the magnetic field at the nucleus is going to be different than the external field. Okay? By the way, this is a very good paper which describes this. He goes through the math really nicely. This is really nice, a beautiful math in this paper as well. Took me a while to get through it because they do a lot of tensor algebra, but it's pretty good. Now, because the electrons in a molecule are not necessarily bound into perfect orbits, you know, they're these hybrid orbitals, they're sometimes multiple wave functions. The electrons are not necessarily moving, sort of like you would think classically. They could be doing all sorts of weird things. Okay, the change in the magnetic field is actually not just in the direction of the magnetic field, it's a tensor, which means it could change in multiple directions. So if I put a molecule in a magnetic field, the external magnetic field could not only be a different magnitude than the internal field, but it could also be in a different direction. Now here's what's really interesting. For chiral molecules like amino acids, the shift is opposite directions. It's always opposite directions. Even in an isotropic medium, even if I just take some kind of medium and I shake it up so that they're all randomly oriented, the shift is always in opposite directions. Okay? So if I have nitrogen 14, the magnetic field for left-handed molecules is going to point in a different direction than the magnetic field for right-handed molecules, which means the magnetization, the number of nuclei that point in one direction, have their spins oriented one way, is going to be different, or rather their spins are going to be pointing in a different direction than right-handed molecules. So now what we've done was we've coupled the nuclear spin to the molecular chirality. Left-handed chirality will result in a spin that points one way. Right-handed chirality will result in a spin that points another way. A lot of little tiny pieces here. A lot of little things going on here. That means if I have some external source like a cosmic ray or an external electron and it's polarized, it's going to interact differently with the left-handed molecule than it will with the right-handed molecule. And this has been studied before. This has been studied at least at the molecular level. We're starting to prepare experiments where we can hopefully look at it at the nuclear level. So for example, if I have some spin-oriented lepton out here, the left and right-handed amino acids are going to be destroyed at different rates. And the reason they're going to be destroyed in nuclear reactions is because the nuclear energy is much larger than the molecular energy. It'll just rip the nitrogen off of the molecule. And that's been studied before as well. Okay? So this is really tricky. This is called the Buckingham effect. So there's a nice paper by David Buckingham. A couple of nice papers if you're interested in looking at it. He wrote a paper in 2006 and 2000. I think he had one in 2009 and 2014. Okay, he's quite old, but extremely intelligent. And also, this is incorporated into modern NMR. So in modern NMR, we can actually look at the shift in the magnetic field in one direction or another. It's quite complicated, but it's a real effect. Questions so far? Okay, and by the way, this shift in the magnetic field, this is called the shielding tensor. What that means is which way does the magnetic field point inside a molecule, okay? That's called the shielding tensor. And in order to calculate it, it's actually a pretty involved process. It's kind of fun because you get to make some really interesting diagrams and images, but it's also quite complicated. So let me show you a couple things here just for fun. On the left-hand side here is a valine molecule, okay? And on the right-hand side, so this is how I look at molecules. This is, you know, with the sticks and the balls, and you put them together, okay? On the right-hand side, this is how a molecule looks, at least in terms of the electron orbitals. The electron orbitals are a probability that the electrons are going to exist somewhere, okay? And so you think of it more as a surface and not so much as you know, an electron is a point in space spinning around. It's more of a probability surface. A cloud, yeah, a cloud. That's exactly it. Yep. The colors, and it's oriented the same way in both diagrams. So nitrogen is here, and nitrogen is somewhere around here. The colors indicate the strength of the shielding tensor from the electrons at this location. Okay. The colors indicate how much the magnetic field is going to shift for the nitrogen molecule, or the nitrogen atom, based on an electron here or here, here. You can see the largest effect comes from the electrons that are closest to the nitrogen. Okay, they're the ones with largest relative effect. Yes, question.
Which is better between this way of seeing molecules and the X-ray crystallography?
Oh yeah, X-ray crystallography is very cool. So with crystallography, you're scattering X-rays off of structures, right? And when you do that, what you're doing is you're looking at the actual which way where the atoms are arranged in the crystal. So with crystallography, you've got let's say I have a simple crystal here, okay? I don't know, like salt or something like that, okay? You know, I bounce an X-ray off it here, and then some of that X-ray beam is going to go down here and bounce off. So their wavelengths are going to be shifted a little bit, so you get an interference pattern. You've seen this, by the way, several times. When you walk outside and you see a puddle of water, and you see like a rainbow on it, that's an interference pattern from the oil on the water. Exact same principle here. Okay. The difference is we have discrete points here, and so this will make a nice pattern on a screen, and you can determine the structure of the crystal.
It is this weird thing that when I take a picture of a screen of a PC, there's this weird pattern. Is this?
It is an interference pattern because I think your computer screen flashes 11 times a second or 60 times a second or something. So your camera, of course, is very fast. When it takes a picture, it might be taking the picture of the screen at when the screen is off, for example, or when the screen is changing. Mm-hmm. It's an interference pattern. It's a different description of interference, but it's still interference. Yeah, crystallography is really cool. Okay, so what do we have so far? Let me summarize where we're at. Okay, so we know that a particle has spin. Okay, we know what the particle spin is. We know what the magnetic moment is. We know nitrogen has a magnetic moment, which means it can be aligned in a magnetic field. We know electrons and neutrinos and muons have magnetic moments. We know electrons, neutrinos, muons have spin. And we know that the interaction between a lepton and a nitrogen molecule atom, nucleus, depends on their relative spin orientation. We also know that in a magnetic field, the nitrogen nucleus has a spin which can point in a different direction for left-handed and right-handed amino acids. So depending on your configuration, you can have a reaction rate between an external lepton and your nitrogen, which is different, which means you can destroy a left-handed amino acid or a right-handed amino acid faster than another amino acid. So we know what a lepton is. All of these pieces come together. They can select chirality in space. This doesn't require chemistry, so doesn't require life. So this can happen in extraterrestrial environments, right? It can also happen on the surface of the Earth because the Earth has a very weak magnetic field. And in fact, we can do magnetic resonance using the Earth's field. So it seems reasonable that nature can do this as well. The Earth also has a really nice source of polarized leptons. You know what that source is? Yep. So polarized electrons and muons. Where do you think? Yeah. Cosmic rays. Cosmic rays entering the Earth's atmosphere can be polarized. And so we've got that source as well. So this could happen in space. It could happen on Earth. Okay. The question is, how quickly can it happen? Yes, question.
Does the sun also produce polarized leptons?
Does the sun produce polarized lepton? Neutrino streaming from the sun, I guess that's the easy answer, right? I suppose I can't remember what the. It seems like electrons streaming from the photosphere might be polarized, but I can't think of a good reason why right now. The reason they're polarized in Earth's atmosphere is because cosmic ray neutrinos or cosmic ray muons, or protons for that matter, interact with the upper atmosphere. And they have a definite, can produce a because of angular momentum and conservation of momentum, can produce leptons that move in one direction with a certain spin. Okay, we also know that all amino acids on the Earth are left-handed. So at some point, if there was something that triggered amino acids to be slightly left-handed or slightly right-handed, somehow there must have been something else which took those amino acids and moved them all in one direction. And moved them all to left-handed, for example. And that process is called autocatalysis. That is actually a very broad field of study in chemistry as well. Chemists spend a lot of time doing this. Significant study in chemistry. There's something else I want to mention, and keep this in mind because I'll talk about it in a little bit. Isotopic abundances in meteorites. Just remember that. I'm going to talk about that in a bit. But what me and my colleagues did was we wrote a model where we just tried to model amino acids in magnetic fields of various magnitudes, very strong, very weak magnetic fields, in fluxes of polarized leptons, so neutrinos and electrons, for example. We started off with neutrinos because even though they have tiny cross sections, they're 100% polarized in one direction. Okay, and one model we came up with was really interesting. This would have been a meteorite flying by a neutron star, which has a very strong magnetic field and is a source of cooling neutrinos, and it emits antineutrinos and neutrinos at different rates, different luminosities. And so what this is a plot of the enantiomeric excess as a function of the radius from the star, what's the closest point that the meteorite flies by the star, and how long it takes to get that enantiomeric excess. And so you can see that after 14 seconds or so, it's very fast flyby. We get up to something like 10 to the minus 4 or so, which isn't bad for this particular model. If we let it run longer, it could go longer. The other thing we're not including is autocatalysis. We're not including any chemical reactions that may take place that could enhance the process. So it's kind of interesting. I mean, it's compelling. It's interesting. I don't know if I believe it or not, but it's interesting. Note that this process also works in Earth's field for cosmic ray interactions. It's a very low rate in Earth's field because Earth's field is very weak. But one thing that nature gives us is time. It's, we can spend a million years processing amino acids and we'll be just fine. Okay, and then there's some other things that we have to consider. Molecular moments and crystallization. Polarized photons could be another possibility, and so we're going to do some of those calculations. Then the one thing we haven't considered yet at this point was autocatalysis. If we include chemical reactions in there, does it help us out a little bit? Can we include a chemical reaction model? And so we just came up with a couple of simple chemical models, sort of toy models, if you will. And we used two of them, and we didn't invent these models. These models exist. This is what we call a divergent model. And what you're looking at here, the black lines are left-handed amino acids. The red lines are right-handed amino acids. And then the blue lines are a catalyst. Okay? Just a separate molecule that helps the reaction. Okay? And so the autocatalysis actually allows us to destroy almost all of the right-handed amino acids while building up the left-handed amino acids here. And so we can go to 100% very quickly. And so this is really interesting. This is a field that's common in biochemistry. We just wrote a paper on this. I guess we wrote it last year. If you're interested, you can look at that paper to figure out how we did that. And then we looked at another model, which is called the convergent model, which is probably a little more realistic. And for this model, we actually assumed a very low magnetic field, like Earth's field, and a very low flux of polarized leptons. And take a look at the time. We're talking about 10 to the 10, 10 to the 11 seconds, hundreds of years, thousands of years or so, which is fine. And there's 3 different models on this page, and you can see the left-handed amino acids still increase in number. The right-handed amino acids decrease in number very significantly. So this autocatalysis can help us out quite a bit. The hard part is not being a chemist. I have to talk to a lot of chemists, and they have to help out with the vocabulary and stuff. That's one thing. Physicists, you know, if I thought it was hard talking to astronomers, talking to chemists is really hard. It's like they talk a different language or something. Now, there's one more thing that I want to mention that I thought was really interesting, and that is, remember when we talked about isotopes and isotopic abundances a couple days ago, abundances of isotopes, okay? We know what the abundance of deuterium is on Earth. We know what the abundance of nitrogen-15 is on Earth relative to nitrogen-14. We know what the abundance of deuterium, carbon-13 is on Earth. It turns out for these amino acids in meteorites, the abundances can actually be different. So a meteorite may have more deuterium relative to hydrogen than on the Earth. And a meteorite may have more nitrogen-15 in its amino acids relative to nitrogen-14 than on Earth. And so one thing we examined was, does our model, because it produces a nuclear reaction, does our model change the abundances of deuterium and nitrogen-14 and nitrogen-15? And the answer is yes, it does. So these red dots, this is a plot of the relative deuterium abundance. So this delta D means relative abundance between deuterium and hydrogen. Delta, this should be N, this should be N, delta N, relative abundance between nitrogen-15 and nitrogen-14, okay? And this is time divided by 1,000, in fact. So deuterium, all these red dots here are measurements from actual amino acids in meteorites. So deuterium, deuterium can have 8 times more, can be 8 times higher in meteorites than on Earth. Nitrogen-15, this is careful, this is divided by 1,000. Nitrogen-15 can be something like 10 or 20% higher in a meteorite amino acids than on Earth. And so it turns out our model is able to do this because it involves reactions at the nuclear level. So we're able to look at things like recombination of amino acids. We're able to look at things like electron capture on nuclei and then rebuilding amino acids. These dotted lines here indicate different models that we did. And so some of our models pass right through the data, which I thought was kind of interesting. I thought that was a kind of a neat result here. We're able to not only produce left-handed amino acids, but we're also able to produce more deuterium or more nitrogen-15 in the amino acids. So I thought that was neat. Then the question is, why would this work? Where would this work? What are different places where this model might work? So we looked at all sorts of places. We looked at orbits around neutron stars. We looked at gases surrounding neutron star mergers. We looked at planets that were really far away from type 2 supernova. We looked at the surface of the Earth. And we got different results, and they're all quite interesting. So this is just a figure. I'll skip that. There's a table in the notes here. I'll just show you here and let you look at it. But there's a table in the notes that shows you how some of the results vary. And in particular, this column, this row here, the maximum enantiomeric excess that we might be able to make with some of these different models. This does not include autocatalysis, however. So this is just as high as it will get without any help from chemistry. what I didn't put on was the recent model we did for Earth's field. But I showed you the graphs for that previously. Okay, so that was a lot of the theory there. One thing we'd like to do is we'd like to try to start doing experiments for this. And the first experiment we want to do is, first of all, see if our calculations about the molecules are right. See if these shielding tensor calculations are correct. And I told you previously, people have already simulated, or people have already experimented on models in magnetic fields using nuclear magnetic resonance. And so what we're doing is we're actually doing experiments with magnetic resonance to try to understand what the shapes of these molecules really are and see how close our calculation got. So this is a diagram of a nuclear magnetic resonance machine. Very, very simple machine. You just put a molecule in a magnetic field, and then you have a separate RF field, think of it as a magnetic field that oscillates back and forth. And what's going to happen is as the spins of that molecule process in the magnetic field, you're going to tune the RF field until you get this resonance. So it's always spinning in the same direction. And then you get a large increase in a signal. What we need to do is we need to adapt this machine so that we can study one particular chiral molecule, and so that we can change the orientation of this molecule within the machine along 3 different axes. So we had to develop something where we put the molecule in here, and we had to develop what we call a new magnetic resonance probe. Here's a machine drawing of it right there. And so on the right-hand side there, this is what we're working on. They actually built this in Germany, and they just finished it. So this will be my Christmas gift. They're going to ship this very soon. But what it is a specialized probe where we actually take amino acid crystals, put them on the end of the probe, and then we can control the top of the probe and orient those crystals any way we want. It's actually really neat because for me, I'm quite interested in the astrophysics, but my colleagues who do NMR, they're interested in this new probe that we've developed. So we're helping each other out. So I'll probably do my experiments here, and I'll probably just leave the probe there so that they can play with for a while. So it's very, very mutual relationship here, very mutually beneficial for both of us. Okay, that was a whirlwind tour. Oh, by the way, whoever asked, this is highly biased in favor of my own research. So whoever asked that a couple days ago, so I should have told you ahead of time. That was a whirlwind tour of sort of what I'm doing in astrobiology. It's a small part of my work, a very speculative part of my work, but also potentially highly rewarding part of my work. So what questions do you have? Yeah.
How does this probe rotate the molecule?
Yeah, that's a good question. So what we do is we take the molecule, we make it into a crystal. I should have brought pictures of the crystals we've made because you have to be really careful with the crystals as well. And in fact, we actually do X-ray crystallography on the crystals. Somebody who mentioned that, so that we can make sure at least the molecules are all oriented the same way. At least they stack up on each other. What happens is there's a little stage down here. You can't see it in the drawing, but it's a little stage that looks like let me try to draw it. It's a little stage that has a plate on it, really. And we put the crystal here. We just glue it on there. And then this stage has a cable connected, what we call a goniometer. Goniometer just rotates things. And so this crystal can rotate around that way. But then this plate is movable. So we can take the plate, we can put it here. We can put it here, so the crystal sits out here, so we're rotating around a different axis. We can take the plate out and rotate it this way and put it in that way, so the crystal rotates around a different axis. So we're able to rotate around 3 different axes. Yeah. What we would like to do is glue this crystal on with an orientation that matches the crystallography orientation. When we do the crystallography, we have a crystal. It looks like a piece of salt. It's tiny, but it looks like a piece of salt. The crystallography tells us which way the molecules are oriented within that block. So I have a block here. I can't see the molecules, but the crystallography tells me which way they're oriented in the block. And what would be nice is if we could glue this crystal on here so that we knew exactly which way the molecules are oriented. That way we can get an actual X, Y, and Z axis. Otherwise, what we have to do is we have to do like a reverse mapping on this thing. We have to map to the NMR frame, then we have to map to the lab frame. Then what we get is we get a tensor. We have to put that tensor through what we call a rotation transformation, a couple different, so that it matches our calculations. It's a lot of math. It's fun math, but it's a lot of math.
Tensor calculus.
Yep. Do you know tensor calculus?
Ricevuto astro, eccetera, eccetera.
Okay. Yep. Came from Italy. Yep.
Devi
Other questions?
la relatività generale c'è stato.
Okay, I have been talking for about an hour and a half, which is about 1 hour longer than I can talk before people start falling asleep. We only have a few minutes left. So thank you all for your time this week, and that'll be it for today. Have a good rest of your week, everyone.
Thanks.
Yep. It'll be pretty easy. A couple simple multiple choice questions. Are they allowed to use notes on the exam? Are they allowed to use notes on the exam?
No, maybe we should give them some.
Oh, okay. Yeah, that's what I'm. But can they bring the slides that I have if they want? Okay, yeah, you can use the slides, like simple calculations. I don't intend on flunking everybody and then going back to America. and never get invited back.
Maybe, are you going to give him a small written exam and then some question?
I think so. That was the plan, right? A couple 4 or 5 simple questions or something like this. Is that okay? It's your class, I think, so.
Yours.
Yeah, but you get to determine who flunks, so they can blame you.
I think we can organize like that. We'll have a small written exam.
I open my microphone so also people at home will understand or listen to me. So
You will have
a small written exam for half an hour.
Yeah, at most. Yeah.
So then we will go on with few questions, direct question, and then we will deliver you the certificate
okay.
of vaccination. No, I mean,
Yeah.
okay. It will, I mean,
So are they allowed to use?
I would say a nasty exam.
To make sure you were listening, just to see if you were listening. So.
Yeah.
Not
Okay.
yeah, that sounds good. Yeah.
A casa avete capito? La mattina alle 9 vi piegate, così fate anche voi l'esame. Ci siete?
A che ora sarà?
Alle 9.
Ok.
Ok?
Presentare?
Aspettate, mi sento. Dite?
Dove ci dovremmo presentare?
Aspettate un attimo. Allora, non ho capito la data dell'esame. Dipende se volete venire in presenza o se lo fate da casa. Insomma, chi è a casa si collega alla rete su questo canale e chi viene in presenza è in presenza.
Ma in che giorno?
Domani,
Ah, domani alle
mattina,
9.
domani alle 9. Ok?
Alle 9 di mattina?
Alle 9 di mattina, sì. Sì.
Ok.
Comunque, ora vi mando un messaggio, ok? Ciao, ciao ragazzi. Allora, alle 9 di mattina l'aula dovrebbe essere